Hey guys, so today I'm going to try a little bit of a different strategy where I'm going to try to record these problems individually. This is the day after the midterm, and none of you guys are here, so it's not the most surprising. But I'm going to try to go through some things that will be related to the homework that you guys have due on Friday, and then I'm going to build up through a series of problems that will build up to some of the example midterm problems that were out of scope for this midterm. So the ones that included angular momentum, which is if we look on our table, angular momentum is L. So this value here, so this L angular momentum, which is equal to the mass moment of inertia times the angular velocity. So we're going to talk about that today. And we are also going to talk about rotational kinetic energy, which is this quantity right here, which is, so it's just this 1/2 ICM W squared. Okay. So um, let's talk a little bit about one mass moment of inertia kind of concept here. We talked a little bit about this last time, but this is the parallel axis theorem. So the parallel axis theorem tells us that if we have some kind of a shape, right, with that we could essentially break up into separate masses. So like say I have this first one, this I center of mass for this uniform center object, and then I have these two other chunks kind of on the end. What the parallel axis theorem tells me is that I can take the I center of mass, right, for my center uniform piece, right? And I can use a lookup table to find that value. And then I can look at these other add-on pieces, right? And just treat them as separate masses and add them to the center of mass piece by taking their individual masses. So in this case, this mass M. So for this object, right, it would be the center of mass would be this IP is equal to ICM plus 2MD squared, right? Because I have two of these objects on the end. I have one here, right, and I have one here. Okay. Um, so for example, there's one problem in your homework where you have a circle and then you have like a bunch of elephants or something on there. I'm not quite sure what it was. Um, so say I have something where I have a circle and then I have a bunch of these random point masses on my circle. We would apply the parallel axis theorem to this as well, right? Where I would have the center of mass of my circle, and then I would include the number of point masses, right? Times the actual mass that they had. And then this R would be the radius that they were away from the center, right? So for the red objects, it would be that dotted line. And then for the blue objects, it would be that line there. So the distance that they are from the center of mass is going to show how much they contribute to the mass moment of inertia. So the mass moment of inertia is the object's resistance to rotation. So it depends on how that mass is distributed, and that will tell us how difficult it is to get that object rotating. So hopefully that makes sense. Okay. So I'm just going to kind of do a walkthrough of kind of some of the other general topics that we'll talk about today, and then I will go ahead and pause this before I start the first problem, and that will be a separate video. Okay, so the equations that we're looking at here. So aside from the parallel axis theorem here, this tells us, so the parallel axis theorem is if we have one main object kind of in our center that we can use a lookup table for, and then we're just adding these kind of separate pieces on. If we have a bunch of point masses in a system, we can model them using this I here, where we just take all of the masses, okay, and we add them together. All the masses times their radius is squared added together will give us the total mass moment of inertia, okay? Once you have the total mass moment of inertia for a system, so the sum of all of the pieces of your system, you can use that to figure out the rotational kinetic energy. So the rotational kinetic energy just basically tells us how much energy an object has when it's rotating. We can use work energy and all of the things that we've learned so far and include rotational kinetic energy as an additional quantity in our system. So if we have something rotating and then we apply some sort of energy to the system and it stops rotating, we can include that in our equations and in our conservation of energy ideas. So, okay. And then this W is just the angular velocity. So this is very similar, right, to what we see for so if we have kinetic energy and this is a translational kinetic energy, we know that that one was equal to 1/2 mv squared. So this is kind of the rotational analog of that. And we can relate the energies of both of these, right? So we could say, like, say an object was moving linearly and then it hit something and it imparted all of that energy into rotational kinetic energy. We could set this linear kinetic energy equal to this rotational kinetic energy. The units for energy are going to be the same. And we're going to see that in some of the problems that we do today. Okay. This is just sort of a general equation about torque. We talked a lot about this. We're going to see some more static problems later. So this is kind of a nice image, I think, of what it looks like when we have a lever arm some distance away. So this is kind of a nice table to refer to. I will post these notes. There's a blank copy up there, but I will also post the solutions. This one we're very familiar with before. We know that the sum of our torques for a system is equal to the mass moment of inertia times the angular acceleration of that system. These subscripts here, z, just mean around the z-axis. So if I think of x and y and going in this direction, the z direction is actually out of the page. So that means that this pulley, in this case, would be rotating around z, right? If z is out of the page, this is the center, right, of that pulley would be through the z-axis. So hopefully that makes sense. Okay, one very important takeaway for this section. So we've done a lot of things where we have these mass moment of inertia problems with angular acceleration, and we have an object that's spinning, right? And we've just been looking at the angular acceleration and the sum of torques to solve these problems. So when we're dealing with kinetic energy and we have an object that's rotating, but it's also translating, which means, say, in our yo-yo problems, right, we had an object that was rotating, but it was also falling through space. So that means that at the same time as it has a kinetic energy, because it is a rotational kinetic energy, because it is spinning, like we talked about a little bit earlier, it's also going to have a linear kinetic energy because it's falling. So it has two things. So if the object is spinning and it's translating, which means that it's moving like in a direction and not just spinning in place, then its kinetic energy is equal to this linear kinetic energy that we talked about, right? This translational kinetic, linear translational. Translational just means like moving across a plane. So it could be like in the x or the y direction. And then it also has this rotational kinetic energy. So it has KER and KE, what do we call? We'll call it KET, KE translational. Okay. So it has both of those, and that should make sense, right? So if we're spinning and we're moving, we have both. We have a linear velocity and we have an angular velocity. Okay. So if you're confused of when to apply it, ask yourself, is there a linear velocity and is there an angular velocity? And if those two velocities exist, then this is likely what we're looking at here, right? This is what we can use. All right. Then we talked about this before also, but there is also a relationship between that linear velocity, right, and that angular velocity. If we have other things in the system that are at angular velocity, sometimes that relationship might change a little bit. But if the only thing that's affecting the linear velocity of that object is the angular acceleration or how much that object is spinning, then we can look at this relationship where we know that the velocity of the center of mass, which means that if I take that center point and I want to know how quickly it's moving, that's the velocity measuring from the center of the object, is equal to the radius, right, of that spinning object times the angular acceleration. So that's the condition when we have rolling without slipping, okay? All right. All right. So I think, and then we also introduced, so torque a little bit here, or sorry, we have torque here. So if we want to figure out the work that's done on an object due to its torque, we can actually use this relationship where we can find the work done by a spinning object if we take its torque multiplied by the change in the angle, okay? This maybe explains it a little bit more in depth here. Over here, this is actually just power. This P here is power. So the torque multiplied by the angular velocity can give you an expression for power, okay? And the total work in the system, we've seen this before, but the change in energy in the system, change in kinetic energy can give us our total work. So in this case, hello, hi.